Hi, I'm Goutham Rajendran, and this is joint work with Mrinalkanti, Ghosh, Fernando, Granha, Jeronimo, Chris Jones, and Aaron Potechin. I'll be presenting the first half of this talk, and Chris will be presenting the second half. So the outline of the talk is as follows. I'll be describing the Sherrington-Kirkpatrick problems and our main results, and then we will describe the main ideas and go into the proof, and then we'll conclude with open problems. So what is the Sherrington-Kirkpatrick problem? In this problem, we are given a matrix W, which is sampled from the Gaussian orthogonal ensemble GOE, and our objective is to maximize the value of x transpose Wx over Boolean inputs x. By Boolean, I mean the entries of x are +1 or -1. And the GOE is just like a random n by n matrix is symmetric, and the orthogonal entries are sampled from the standard Gaussian n01, and the diagonal entries are sampled from n02. And this is an important problem considered before in computer science, where it can be viewed as an average case max cut problem, and also in statistical physics, where this problem can be viewed as minimizing the energy of the physical system. Okay, so what is known about this problem? First, let's say that I define opt of W to be the true optimum for the matrix W. Then it's easy to see that the optimum value of W is at most twice n raised to 1.5 with high probability. This is because from random matrix theory, when W is sampled from GOE, W has maximum eigenvalue twice n raised to 0.5. So this is and since in this W we are only optimizing over Boolean inputs x as opposed to all inputs x, we have this very simple upper bound. The true optimum is actually close to 1.52 times n raised to 1.5. This was conjectured by Parisi and proved by Talleyrand. Okay, and this is what I call the optimization problem, where we're given W and we want to maximize this quantity. Recently, an algorithm by Andrea Montanari, provided like an arbitrarily good approximation algorithm in polynomial time for this problem. In this work, we're looking at a slightly related problem that we call the certification problem. In this problem, given an input matrix W, our algorithm should give an upper bound to the true optimum, such that when W is sampled from the Gaussian orthogonal ensemble, our upper bound should be as close as possible to the true optimum with high probability. Okay. So in the rest of this talk, we will be focusing on the certification problem. One obvious algorithm for a certification problem is to just output the maximum eigenvalue of W. Okay. And this is what I call a spectral certificate, and this is close to twice n raised to 1.5 with high probability. So the question now is, can other certificates do better than this naive spectral certificate? In particular, you can ask if the SumofSquares hierarchy can do better than this spectral certificate, and can it actually get close to the true optimum 1.52 times n raised to 1.5 with high probability? Okay. So what is the SumofSquares hierarchy? SumofSquares hierarchy is basically looks for a refutation proof for a system of polynomial equations. Okay. So there's a parameter D, and SumofSquares hierarchy of degree D looks for a degree D distribution of solutions for a system of polynomial equations, and it exists if and only if no degree D refutation exists. In other words, if a distribution of degree D exists, it means that SumofSquares of degree D thinks that the system of equations is feasible. Okay, and there's a related dual view to this hierarchy, where you can think of the SumofSquares hierarchy as giving a series of convex expressions to a polynomial program. And using standard semi-definite programming techniques, you can actually like solve this relaxation in time n to the order D. And this is good because this actually SumofSquares is good because it obtains state-of-the-art algorithms for a lot of problems, including maximum CSPs and PCA. So in particular, for our problem, we can ask how does SumofSquares do. Okay, so what is known about this SumofSquares hierarchy for this problem? Degree 2 SumofSquares has value twice n raised to 1.5. This is actually like just as good as the spectral certificate and not better. A couple of concurrent works recently proved that degree 4 SumofSquares also doesn't do any better. And recently, degree 6 SOS also has, it was shown that degree 6 SOS also has value twice n raised to 1.5. Okay. So in this work, we argue that for some small constant delta, degree n to the delta time delta SOS still has value close to twice n raised to 1.5. In particular, this rules with polynomial time algorithms which are based on SOS for this problem. So here's the outline of the proof. We first reduced the Sherrington-Kirkpatrick problem to a related problem called the planar Boolean vector problem. This was done in like a work by Mohanty, Raghavendra, and Shiv. And then we look at like a slightly related problem called which we define to be the planar affine planes problem. And for planar affine planes, we give a direct SumofSquares lower bound, and this goes via 2 steps. So the first step is where we construct a candidate solution. For this, we use technique known as pseudo calibration. And for the second step, we actually prove the positive semi-definiteness of this Moore matrix n. So what's the planar affine planes problem? In this problem, we have 2 parameters n and m, and m is larger than n. You can think of m as n raised n square or n raised to 1.5. Okay. the input is like m random vectors d1 to dm sample from the Gaussian input. And we want to prove that there is no vector v such that inner product of v comma du square equals 1 for all u. Okay. And the reason that we call this planar affine place is because, if this is true, then this means that all the input vectors d1 to dm lie on two affine planes. Okay. If this system is feasible. Okay, so this reduction from planar affine planes, from Sherrington-Kirkpatrick to planar affine planes also carries over in the SumofSquares framework. Okay, and then what is left is we can just prove that if m is what we prove is that if m is at most n raised to 1.5 minus epsilon, then with high probability over the random input d1 to dm, degree n to the delta sum of squares thinks the system of solutions is feasible. Okay, and this means that in particular, because of this reduction, you cannot use sum of squares to optimize Sherrington-Kirkpatrick or provide a certificate for Sherrington-Kirkpatrick problem. Okay, in the rest of the talk, we'll be focusing on SumofSquares lower bound. Okay, so in general, when you want to prove SumofSquares lower bound for a problem, what you would do is you construct a degree D to distribution of solutions, and this is usually for Boolean optimization. This is specified by pseudo moments e tilde of b raised to s for all subsets s of size at most d. Okay, and then you can extend e tilde to all polynomials of degree at most d by just using multilinearity. In our case, we have the input to be d1 to dm, and our polynomial constraints are b comma du square equals 1, and we take d to be n to the delta. Okay, so again, this is what we are proving in this work, and in our particular case, we need to specify e tilde of v1, e tilde of v2, v4, and e tilde of v sub b raised to s for all subsets s of size at most d, such that they satisfy some constraints. In particular, e tilde of 1 should be 1, and e tilde of b comma du square equals e tilde of 1, and so on. Secondly, e tilde of g square should be non-negative for all polynomials g of degree at most d over 2. This is what is called a positivity condition. Okay, and this is usually like the most difficult part of like SumofSquares lower bound proofs. Okay, the second condition can be viewed like this, alternatively like this. If you construct the so-called moment matrix where the rows and columns are indexed by subsets of 1 to n of size at most d, and you define for subsets I comma j, the entry I comma jth entry of this matrix is e tilde of v raised to I times v raised to j. Okay, then the second condition is equivalent to saying that this moment matrix is positive semi-definite. Okay, so we start with pseudo calibration. Pseudo calibration is a heuristic that was introduced by this Barak et al. In 2016, which gives a way to consider candidate pseudo expectation value operator. Okay, roughly when we apply this heuristic, we get the value of e tilde of v raised to s to be summation c alpha h alpha. Here h alpha is the basis of Hermite polynomials, which is analogous to the Fourier basis, and c alpha are actual real numbers that come out of this technique of pseudo calibration. So in our setting, c alpha is non-zero if and only if it satisfies some nice structural parity conditions, and then like in those cases, c alpha is approximately n raised to minus size of alpha over 2. Okay, and by virtue of this pseudo calibration heuristic, this pseudo expectation operator approximately satisfies all the constraints. Okay, so the main difficulty boils down to checking if the moment matrix is positive semi-definite. For this, we use the idea of graph matrices. Okay, so if you look at a specific Hermite polynomial on the input, input d1 to dm, let's say we look at h1 of duui, h times h1 of duj times h2 of duk. You can equivalently represent this as like a graph on 4 vertices. Here, I use 2 types of vertices. One of them is a square vertex, which are written ij and k in this diagram, and the other type is the circle vertices, which is u in this diagram. And I actually have labels on the edges to say what is the degree of the Hermite polynomial that I'm considering for that input entry. Okay. So this gives a natural correspondence between like graphs and Hermite polynomials. Okay, so it turns out that if you look at the pseudo calibration coefficients, what really matters is not the indices on the actual vertices, but just the shape of this graph. Okay. That means that you can actually add over all possible assignments of indices to these shapes, and combine them into one big matrix. That is what I call like the graph matrix. Okay, that motivates the definition of the graph matrix. More formally, graph matrices are functions of their matrix valued random functions. Matrix valued functions of random inputs d1 of the input d1 to dm, And like each so they can be represented by bipartite graphs, where like you have square vertices and circle vertices, corresponding to different kinds of input entries, and sorry, so square vertices and circle vertices and edges correspond to different inputs, and then like each edge has a label which denotes the Hermite polynomial itself, and there will be two special subsets of vertices, which are the blue subset of vertices and the red subset of vertices. They kind of tell you which row and column it corresponds, the matrix corresponds to. And you just to define the entry of oh, by the way, the purple is just like appearing in both U and V, sorry. And this matrix is defined to add over all possible assignments of indices to these vertices. Okay, and here's an example. Like let's say we take beta to be this specific 5-vertex shape with 2 blue vertices and 2 red vertices. Then this corresponds to a matrix whose rows and columns are indexed by let's say subsets of size at most 2, and the ij comma kl entry for ij kl being distinct corresponds to the sum over all possible Hermite polynomials with these corresponding indices, right? So here u corresponds to the circle vertex in the middle, and that's why you have the summation. Okay, so like with this, this generalization, this definition can be generalized, and it gives rise to the concept of graph matrices and beta for every possible shape beta, and you can decompose the moment matrix into like these graph matrices, and that will be the starting point of our analysis. And each m beta has like a coefficient corresponding to the shape of beta. You can think of it as roughly having 1 by n raised to e of beta over 2 coefficient. Right. So why is this decomposition useful? Turns out that graph matrices have some nice norm bounds. This was shown in a paper by An et al., which says that the norm of m beta is upper bounded by a combinatorial quantity, which stems from so-called minimum weight vertex separator of beta. Okay, and you have some sort of norm bounds for m beta, and turns out that this is the only property of the random input that we need. Which means that if you take any other input, like for example like random spherical vectors or so on as the input of the original problem, as long as these kind of norm bounds hold, the same lower bound should hold. Okay. Turns out that graph matrices have another nice property, which is like if you multiply 2 graph matrices, you can always decompose them into a linear combination of other graph matrices, and we use this property like very crucially in our analysis. So now Chris will present the rest of the ideas that go into the proof of this.
Hi, I'm Chris, and I'm going to continue the presentation with the proof sketch of PSD-ness. So to recall, I've written here the expression for the moment matrix that we developed in the last couple slides in terms of shapes. And to develop some intuition for it, recall that the moment matrix breaks into different blocks where each block corresponds to the degree of the moment. And the shapes live in the different blocks of this moment matrix. For example, here are a couple shapes, and here are the blocks they live in. And the block that a shape lives in corresponds to the size of the left and right set of the shape, that being the blue and red, for a reminder. Okay, one observation we can make about this expression is that it has identity matrices on the diagonal, which are contributed by the following shapes. These purple shapes, which have some square vertices and no edges. However, it's not true that the moment matrix actually has ones along the diagonal. There are other shapes that contribute to those entries, but they end up being small, as we'll see. So here's one trivial attempt at proving PSD-ness that we might try. Suppose we could show that if you added up all non-identity shapes appearing in the expression for the moment matrix, their total norm was little o of 1. And this would clearly imply that M is PSD. Well, for some of the shapes that appear in our expression, we can actually do this strategy. Using the norm bounds that I've put up here in the upper left, let's estimate the norm of this shape here. So a minimum weight vertex separator for this shape is either the blue square or the red square. After removing that square, there are 4 squares left and 2 circles. So the norm bounds imply that the operator norm of m sub beta is mn squared for this shape. The coefficient that this shape appears with is 1 over n squared because it has 8 edges. So therefore, the contribution to the sum is actually m over n squared, which, since we assume that m is less than or equal to n to the 1.5, this is little o of 1. Okay, but other shapes do not contribute only little o of 1 to this summation. For example, this shape here. The coefficient it comes with is 1 over n squared, since it has 4 edges. And for the norm bounds, the minimum weight vertex separator is going to be just the circle in the middle. There are 4 squares remaining, so the norm is n squared, and therefore the contribution is going to be omega 1. So towards understanding these shapes that contribute a lot towards the sum, first we should try and classify them. Let's make a definition. A spider is a shape which has 2 degree 1 squares in either the left side or in the right side, which are adjacent to the same circle vertex. For example, these are 3 spiders here. The right shape is one that doesn't have a right side, and you could take any pair of square vertices from that shape to define a spider. And what we're able to show in the paper is that the total norm of the non-spiders is little o of 1. That is, if you add up all the non-spiders and non-identity matrices, you only get a little o of 1 contribution to that sum. For proof, we use the norm bounds plus a charging argument. See the paper for the details of it. So basically, the only thing we have to worry about are these spider shapes in the sum for M. Let's take a step back here, actually. It turns out that this moment matrix actually must have these terms with omega 1 norm. And that's because it has a null space. And the null space is actually induced by the constraints inner product of v du squared is equal to 1. That is, any moment matrix which satisfies these constraints must have a null space. And to see that, I claim the following vector lives in the null space of M. Here, it's a graph matrix, but I've fixed one of the vertices, the circle vertex for u, and the square vertices are allowed to have varying labels. So to recall a little bit more, here's how it can be interpreted as a vector. It's a sum of 2 shapes. The shape on the left lives in the degree 2 block of the vector. The shape on the right lives in the degree 0 block. And what happens if you multiply this vector with M, the moment matrix? Well, if you look at the top row and do some simplifications that aren't so bad, then the top row is actually just equal to the pseudo expectation value of this constraint. And what that means is that this vector lies in the null space of the moment matrix if and only if the moment matrix satisfies this constraint. Okay, here's a trivial observation. It suffices to prove that the moment matrix is PSD on the complement of its null space. Well, it turns out that spiders actually interact extremely nicely with the null space of the moment matrix. And because of the following diagram, consider this spider and factor it across its middle circle vertex. And actually, the thing that appears on the left side is very similar to the null vector that was on the previous slide. And what that means is that these spiders contribute basically nothing on the complement of the null space. They're orthogonal to any vector which is orthogonal to the null space. So all the action of any spider is on the null space, and they're essentially 0 on the complement of the null space. So therefore, by restricting to the complement of the null space, we only have non-spiders and identity matrices, and therefore we are able to show that all eigenvalues of the moment matrix on this complement of the null space are 1 plus or minus the low of 1. So that's the high-level proof strategy. By looking at the complement of the null space, we're exactly able to kill off all the terms with omega 1 norm. It's a rather interesting high-level strategy in that just by looking at the constraints of the problem and expressing them in terms of graph matrices, we get the exact same set of graph matrices as the set of graph matrices that have large norm that appear in our pseudo-calibrated expression for M. And this allows us to exactly kill these matrices only. So finally, I want to say a little bit more about the proof of this theorem and some of the details that go into it in these approximations here. When we remove a spider from the expression for M on the complement of the null space, we actually introduce a couple smaller graph matrix terms in the summation for M. And some of these smaller terms that we introduce might be smaller spider shapes. So what we must do is recursively kill these smaller shapes until we're only left with non-spiders in the expression param. And doing this, we produce what we call a web of shapes for each spider, which is the set of non-spiders and spiders and non-spiders that appear when you attempt to kill off this spider. And the leaves of the web are the non-spiders that finally appear after you successfully kill off the spider. Finally, what we show is that if you consider all the spiders together and all their webs, then that gives some new coefficients on the non-spiders, and those coefficients don't get too large. The total norm, if you add them up, is still little O of 1, which proves that since there are identity matrices along the diagonal, the resulting matrix has all eigenvalues within 1 plus minus little O of 1. Finally, I want to end with some open problems. The first open problem is to figure out whether or not Montanari's optimization algorithm can be interpreted as rounding some SOS solution. So what we show in the paper is that SOS, the value of SOS is 2 minus little O of 1. But this doesn't rule out the possibility of a rounding scheme that achieves basically the optimum value. And it would be interesting to see if Montanari's algorithm can be interpreted in this way. The second problem is to think about average case sparse max cut. So the Sherrington-Kirkpatrick model corresponds to dense max cut on the complete graph with Gaussian edge weights. It'd be interesting to prove SOS bounds for sparse max cut as well. Finally, there's 2 other technical open problems that arise from this work. The first is to improve this assumption n less than or equal to n to the 1.5, n less than or equal to n squared. And the second is to improve the SOS degree all the way up to the conjectured optimal n over log n. The techniques we use in this paper, graph matrices and pseudo-calibration, basically seem unusable to prove an SOS bound this strong. It'd be very interesting to develop some techniques that allow proving a bound as tight as n over log n. Okay, that's it. Thanks for listening and hope to see you at the conference.